Hey everybody, this is Larry. This is Thursdays and on November 24th. So happy Thanksgiving for everyone who's celebrating. Hope y'all have a good turkey and whatever it is that you like eating. Uh, in my family, actually, we usually just get a chicken because we family's a little bit smaller, so turkey is kind of big. And yeah. Anyway, I hope everyone's just enjoying, the long weekend and so forth. I mean, I guess if you're American, if not, then hope the end of the week is coming soon for you. Um, yeah, today's problem is 907, sum of Subarray minimum. So let's get started. Also, let me know what you think about the World Cup so far. So many upsets, huh? Poor Argentina, but yeah, I'm excited to see Americans and the English tomorrow, so we'll see. Yeah, anyway, to get back to today's problem, is 907, sum of subarray minimums. Given an array of integers R, find the sum of min B, where B ranges for every contiguous subarray of R. Since answer may be large, return the answer modulo. Okay, so this is basically return the sum of, oh, oh, okay. So I missed. Wow, this is kind of a tricky problem for medium, isn't it? Maybe not. Let me think about it. But and n is 3 times 10 to the fourth, so obviously you can't do an n square algorithm. Just to double check that, because then that would make it kind of silly, and also then we can go home and sleep. But okay, so these kind of problems where you have to kind of do every subarray thing. Maybe even subsequence, depending on how the problem's constructed. Though this one is subarray and not subsequence. The first thing to do is, well, actually, the first thing I need to do is sing the mod song, because I mod, because I always forget mod. It's not a real song, but I try to put it before, because otherwise I forget. Okay. So the question is, just the idea here is kind of go for it. See if you can come up with a way to construct it backwards. And what I mean by that is that there is an answer, right? We don't know what it is. And in this case, we're trying to figure out each number, how much it contributes to the answer, right? So that's basically kind of the logic that we're trying to get through here for a problem like this. Whether this is apparently subarray mins, but there are other problems like subarray the subarray sums, right? For example, if you want to get the sum of every subarray, not just the minimum, then you have to you may think about how many times 3 appears in different subarrays, right? And in this case, this 3 would appear in 4 of them. 1 would appear in 1 times 2 and so forth, right? So that's just regular sum. Now we're trying to figure out the minimum version of it. And then the question is, and there are a couple, I think there is also, there is apparently I haven't solved this before yet, but there was like a Q4 on one of the contests not that long ago, and I struggled with it a bit, even though I think I got it at the end. Maybe I'm wrong, I don't know. But because I was looking at it, because there are a couple of ways you can think about it. And the tricky thing is about unique elements. And I think that's the problem, that sometimes it's hard, because you can think about it both ways. Like we said, and in this case, and actually in both example 1 and example 2, there are no duplicate elements. But let's say we do have duplicate elements, right? Then what happens? Well, it is more precisely, what happens is that, well, you can this contribution, like let's say we have this as a subarray. Well, if this is a subarray, that means that how do you're gonna say, hey, the left one is a min, and so it should be added 1 to the answer. And then the second thing is that when you process the second one, you're like, oh, that one's also the min, we should process the answer. But now we've seen that we can't do that, right? So we have to figure out a way to kind of keep it consistent. Okay. So, the first thing that I would do is kind of think about, still think about it first. Mm. Let me think about this. I mean, there are a couple of ways I'm thinking about it, but wow, this is kind of a hard one for medium, right? All right, I think that gives us something to think about. But let's actually go back to the basic first, right? So in this case, then I think all we have to do is try to find kind of the boundaries of the next smaller number, and then the previous smaller number, and then those are the boundaries of your things that it can be the min, right? So in this case, for example, 3 has no movement of freedom on the left or the right. 2, we can actually go extend. I mean, this is a very small. Let me try the other one because this is a 4-element array, so it's a little bit hard to illustrate. And this one is a mountain, so it's kind of bad as well. So okay, fine. But let's say we have something like, I don't know, like this, right? The 2 goes all the way extended to the, and this is still a mountain, but let's just say we have another 5 here, right? And the 5 here, the minimum that goes to the left is 4, so we have 2 choices to the left and 2 choices to the right. Well, technically 3 because it goes from 0, 1, and 2. So that means that 5 will appear within 9 subarrays, right? So we can kind of just sum that up, right? So for example, and what I mean by that is that let's say 3. How many subarrays does it appear in? It appears in 1. 1 appears in all of them, really. So on the left, it has 2 degrees of freedom, meaning 0 and 1. The index 0 and 1 to the left. And here there are 3, 4, 5, 6, 7. So what is it? Did I say 7 or 8? 7, so there are 8 degrees of freedom, so 2 times 8 is 16, right? 2 just to the right, and I think there's 6 left, so there's 7 degrees of freedom. 4, same thing, but 6. 11 is, oh no, I lied on, oh no, yeah, 11 is fine. 11 is 0 and 1, so that's 2 on the right. 5, you can go 3 on the left, 3 on the right, so that's 9. I mean, I may be off here, but I'm just using an example, right? Oh, actually, this goes 2. So then now you sum all that up and multiply, sum it up, and then that's pretty much it for this one. That's the idea. I'm trying to see whether, yeah, I mean, the tricky part, of course, is the now I think we're fine here, except for, of course, you have to do some math, because if we do it naively, this will be n squared. So we have to kind of, we have to do some kind of, we have to do some problem here. Wow, this is kind of really hard for a medium, isn't it, huh? That's kind of, am I missing something weird? But yeah. But that's pretty much it. And there, for this one, assuming that there are no dupes. But what if there is a dupe, right? Then we have to kind of figure out, like, legit. Let's say we have multiple, ones or whatever. And we'll skip all the numbers. So here, 1, the first one, what are we doing, right? So there's 2 degrees of freedom to the left, and then let's just say 3 or 4 degrees of freedom to the right, right? Okay, maybe that works. So second one, here, I'm trying to think. So one way to kind of resolve these kind of uniqueness is introducing a sort of asymmetry with respect to the left and the right. And in that, you guarantee that in overlaps, someone else, quote unquote, the later numbers would pick up. And what I mean by that is that here, for example, for this one, you have 5 numbers to the left, so maybe there's 6 degrees of freedom, but to the right, it only goes up to 3, because you assume that any numbers that includes this one, the one on the right that comes later will get taken care of by that number. So in this way, it is symmetry breaking, if you want to call it that, even though I know that means something else in physics, and it's always cool to say. So yeah, so that's basically the idea, and then now you can do the same thing. And it's something that comes up here and there. I think this works here, but yeah. And it's something that I think I struggled with the Q4, but this is kind of a really hard form. Okay. So now that we break it down this way, so what did we do, right? Again, if we do it naively, it's going to be n squared. So then here, for each, let's just write it out, right? For each number, we want to find or how do I say this? All numbers, or we want to find the number of numbers that are smaller to the left, you know, until the break, right? And smaller or equal to. And also for each number, we want to find the number of numbers that are strictly greater than, right? To the right. Equal to the right. Okay, I guess maybe that's just very awkward phrasing with the two twos. But okay. The reason why I want to write it out is because now we can see if there's a linear time algorithm for it. And you know, I think this is, yeah, I think that's pretty much it, right? And this is where, you know, we introduce our good friend, the monostack, I think. Oh, maybe, yeah, monostack. Because basically the idea here, and I this is kind of a hard problem, and I don't know if I have the energy to really go over monostack in a very deliberate way. But the idea here is that, okay, let's just say we, oh, I wish I've kept that away. But let's just say we have here, right? And then maybe just, again, I don't know. Then the idea behind the having a stack is that, you know, we go 3, we go 1, and then 1. Yeah, so when we process the 1, we know that every number after that, it either is going to be bigger than 1, and therefore stopped by the 1, if you will, stop the streak. Or if it's smaller than 1. If it's smaller than 1, it's going to be smaller than 3, so then we can pop. So that's basically the invariant that we're keeping. And because now, let's just say we build it up, and the stack is now 1, 2, and 4, and then now we try to put in a 3. And the 3 is smaller than a 4, so we know that, like I said, in the future, if a number comes in, if it's smaller than 3, it's going to be, you know, if it's smaller than 3, it's going to be smaller than a 4. If it's bigger than a 3, then it stops anyway. So therefore, the 4 is not necessary. And in this way, you have this monostack, named monostack because it's monotonically increasing, though that's an emergent property of the invariant that we're trying to keep. And of course, the key part about keeping this monostack is that each number will only be pushed and popped once, and therefore it'll be linear time. And as a result, that is basically yeah, that's basically it. So yeah, okay. So let's kind of start implementing that then. We'll do the first part first, and then we'll kind of see. And we might just generalize it a little bit, but yeah. So for x in arm, okay, if length of stack is greater than 0, and here the stack will contain, I guess we should have kept the index, right? And the value is greater than, so basically if it's the same, we want to pop it off. Yeah, we want to pop it off because we want to keep going. Okay. So yeah, so if the stack is greater than or equal to, then stack.pop kind of, but previous I guess previous x doesn't matter, but yeah. Let's just say pi is equal to I, say, right? Basically here we're just trying to go back to see how far the index goes, and then once we pop, and then at the very end we append back pi x, right? But before that we want to, okay, let's just have a total. Yeah, and then here basically we want to add so x appears how many times? So pi minus I plus 1, I think. Is that what I want to say? I may be wrong on that one. Yeah, and let's kind of see how this looks for now. Not super confident about, I mean, it's definitely not right because we didn't do the other side yet, but let's kind of, you know, run it, and because basically we're just doing a little bit of a sanity test as well, in the sense that, you know, if the number is bigger than the input numbers, like for the test case, if, for example, if I got like 500, then I know something else is really wrong. Oh, whoops. I know that something is really wrong because no matter what, it should be less than 400, right? Okay, so I expect that the number is smaller, and it looks pretty okay so far, actually. So yeah. And the other thing that we can, of course, do is just verify by hand, right? Meaning that if you really want, you can also just write another for loop, I mean, for small cases, and even you could put in more cases to check for small numbers whether this is true. And this is just going one direction, so we haven't gone the other one yet, so we know that this is wrong. But 3 appears 1, so that's going to be 3. 1 appears twice, so that's 2, so that's 5. 2 appears just 1, so that's 7, and then 4 appears 1, that's 11. Did I say that well? So 3 plus 2 is 5, plus 7 plus 4 is 11, right? That seems a little bit off then. Hey, all right, let's see. Oh, do I have to care about this? The stack at the end? I don't know. 1, 2, 4 sounds right, but all right, let's see. So yeah, so this is just sanity checking what we think the code should do and what the code actually does. So 3. Okay, so this is, we popped this. Oh, I got the direction wrong, though. It's a little bit awkward, but okay, fine. Because the previous I is the smaller number. Okay. Okay. So now this is 11 as we kind of calculated manually, and still within range. So like I said, this is why we kind of debug these one at a time sometimes, especially when you're not super confident about it, so you can kind of spot these things as it happens. Okay. So then now we just have to go backwards and do the other side, I think, right? Do we? We could also maybe, when we pop, we add some numbers. Does that work? No. I don't know. Well, let's not try to be too clever for now, and then we'll go for it. So for I, X, and enumerate, in this case, we're going to reverse the array because we're going from right to left, and then we just do the same thing. Oops, that autocomplete is weird. But in this case, now we want numbers that, we need the numbers that are smaller. You can kind of prove it at home, maybe. I think this is maybe a little bit off by 1. The reason why I say that is because I think we I think this is a little bit off, but I'm gonna just spin it real quick. The reason is I think we're double counting X in both cases, possibly. So yeah. Maybe that's good. Nope. Okay, so looking back, oh no, the logic is still the same. It's just okay, that's why. Because I think I played in my head a little bit too much thinking about the symmetry. Do I need to do this? I don't know. But because of the eco, we just have to not care about the eco signs, I think, is the idea. But but it's still wrong though. So let's kind of think about again. You know, now we can debug it, knowing that this part is what we expect. So then we don't have to worry about playing around with debugging. So for that part, but for this part, we have to. Sadness. Okay, let's see what magic it is doing. So it goes to 4, okay. I mean, it doesn't do anything because it already counted on the left. So okay, fine. And then I think I know what it is. I think I just did this in a silly way. Because I think I premature. Because I think I was hoping that that wasn't the case, but I think I did made a boo boo here. And what I mean by that is because the formula is actually, as we kind of go here, for example, the 3 is actually the number of degree of freedom to the left, to the left, and times the number of, let's do this one. It's the number of degrees of freedom to the left times the number of degrees of freedom to the right, right? But what we have here is that I kind of delineate them or dequadratic them a little bit for some reason. So I think this is just super wrong. But what we can do is do something like this, and then left dot append I minus pi. Do I do +1? I think +1 actually. Yeah, okay. And then now when we go to here, whatever. So I was going to write something more clever, but yeah, let's just do this, and then write dot append I minus pi +1, because this is a little bit funky because everything is reversed, so I didn't want to whatever. So now we can reverse the right, and then for for x, I don't know, left right in sip of r, is it? Left right, and then whoops, did I have that on top? Well, I guess I did have them on top. So then we add L times right times x, and then mod it, right? That's basically the idea. Hopefully this idea is right, because otherwise it's just silly. I mean, I may be off by 1, and that's fine. But okay, so it works for here, but not here. Why is that? Now let's kind of give it a spin real quick. A lot of debugging today. Maybe I got the indexes wrong. 11, this is clearly already wrong. The right should be more than 1. Did I do it in the wrong order? That is weird, actually. Because right should at least be like 4 or something. So the right part is wrong, but the left part is right. Why is that? Okay, so it starts with the 3. That's good. 0, 1. 90, okay, the 81 should be popping. The 81 should pop the 94. Oh man, wow, this is just really wrong. I'm just being really dumb. It's. How did that even pass before? What a silly mistake. Okay, now there we go. I guess this one just. I don't know. sometimes code has a way of being right for totally the silly reason. Because it got 11 here, right? That is really weird. Okay, but yeah, silliness aside, let's give it a quick submit and hopefully not super long. Yeah, first time solved, 969-day streak. Yeah, as you can see, this is going to be linear time, linear space. Hope I don't have to go for that part just because I think this is pretty straightforward with respect to that one, in that, you know, the space is always is linear. We reversed it a few times and even zipped them, but everything is linear. In terms of time, we just, like I said, each number will be popped and pushed once at most for the left, and then also once again for the right. So that's going to be yeah, linear time, linear space. I think this is a hard enough problem for me to kind of, you know, hang my Thanksgiving on. So let me know what you think. This is definitely not an easy problem. I don't. I mean, it's definitely not an easy problem, but it's also not. I think it's a little bit on a harder problem for medium. Though I mean, if for people who are very practiced, they could get this very quickly. But yeah, let me know what you think. Stay good, stay healthy, to good mental health. Happy Thanksgiving, everybody, and you know, hope you have a lot to be thankful for. Let me know in the comments what you're thankful for this year. That's all I have, though. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.